Evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to part two now. We'll be doing part two of this training video, and we're going to continue our discussion on pressure and temperature advection. So let's get right to part two. And we're going to begin part two by talking a little bit about cold air advection and what that is. Simply put, cold air advection is the flow of air from a colder place to a warmer place. Temperatures are depicted on weather maps as lines called isotherms. ISO literally means equal, and therm means temperature. So these are lines of equal temperature, how we depict different types of temperature advection. Now, when winds cross these isotherms, or lines of equal temperature, there is some sort of temperature advection taking place. And I'll show you an example of this here soon. With cold air advection and the air column. Now, when I talk about an air column, I'm talking about going from the surface and up an elevation above the surface. So since colder air is denser, and we've learned this already in my past training videos here, cold air is denser and it tends to be sinking more because it's denser or heavier. It sinks. And with that, with cold air, the upper level heights will then begin to fall. Sinking air will then initiate what's known as downward vertical motion. So we have sinking air motion in the atmosphere, which in turn then sets up this upper level convergence or convergence aloft. And we talked about the damper effect before. I'll show you some examples here in a moment. Now, this is going to result when we have upper level convergence at the upper levels of the atmosphere aloft and sinking downward vertical air motion. That is going to result in higher surface pressure. And with cold air advection, we see upper level heights generally fall. That's kind of a repeat of the first bullet up here. And then surface pressure rises. All right, so let's examine this graphically, okay? All right, so let's take a look at this. All right, first thing first, CAA is the abbreviation for cold air advection. This would be our atmospheric column here, okay? So again, when I'm talking about atmospheric column, I want you to think about from the surface all the way above the surface to higher levels in the atmosphere vertically. This would be your air column here, okay? Now, with cold air advection coming into the air column, so we have colder temperatures moving into our air column here, our vertical air column. What is this going to do? Okay, with cold air advection, it's going to cause these upper level heights to fall. And why is that? Because this air, this colder air up here in the upper levels of the atmosphere, I'll abbreviate cold air with a C. It is going to result in sinking air motion in the upper levels of the atmosphere, and that is going to result in these upper level height falls. When we have cold air advection in the upper levels of the atmosphere, the heights are going to fall. The air is denser, it wants to sink. For surface pressure rises, think about this. We put cold air advection close to the surface. You know, we got this C letter here. This represents your colder air at the surface. Additionally, we get this upper level convergence, this damper effect. And we get downward vertical motion as this air is sinking from the upper levels of the atmosphere downward towards the surface. And that's going to result in surface pressure rises. I want you to think about it like this. All right, so let's just go off to the side here and I'll draw this out for you. All right, so imagine we have cold air advection, okay? The upper levels, those heights again are going to sink. The upper level air here is going to converge. So you see how these air streams are kind of meeting here. And then the air is going to sink. We're going to downward vertical air motion, okay? Now imagine this is the surface here, all right? Sinking cold air, it's heavy, dense. This is our surface. What do you think is going to happen right here on the surface? When we have downward vertical motion of air, that's going to add more force per unit area here at the surface, and that's going to result in rising barometric pressure. Now, what happens when we talk about troughs and colder air advection or colder air moving in? What do you think is going to happen here? Let's examine this. If cold air it moves into the base of a trough, the trough is going to deepen. So you see this picture here on the left. Notice the solid black line. Now that solid black line represents your trough, your upper level trough. This solid thinner black line represents your upper level trough axis. So the trough axis is here. Remember, the trough axis is the point at which you have your lowest heights, your lowest pressure. Okay, so we got this blue oval here, and it's basically moving through this trough. It's moving through this trough here, and it's going to result, colder air injected into a trough is going to result in this trough deepening. Now, when I say deepening, I want you to think about this, okay? All right, so I'm gonna give you two examples of a trough. Now my line's gonna be in red here, solid red, but imagine this is a trough, okay? Now you inject cold air on the back side into the base of this trough here, okay? That is going to result in this trough deepening. All right, so deepening really is described as the amplitude of the trough increasing. And amplitude is simply basically half the vertical distance from the base of the trough to this subsequent ridge. And so this is known as the amplitude. It's basically right here. It's 1/2 of this complete troughing, the amplitude of the trough. If we steadily increase the cold air, it gets put into the base of this trough, it will continue to deepen, or that trough is going to dig. As the trough deepens or digs further, again, it's going to increase in amplitude. And that's, again, amplitude is going to be 1/2 that vertical distance of the trough. All right, as the trough deepens, what's going to happen? It's going to slow in speed. So colder air into an upper level trough is going to deepen the trough, okay? Let's say initially up here in the upper left, this trough is moving towards the east at 25 knots. But now the cold air has made it into the base of this trough, to the trough axis. It increases the amplitude, makes this a deeper trough, and then the speed of the trough as it propagates or moves to the east is going to slow down. So the deeper the trough, the slower the speed of that trough. What happens now if we take cold air advection or bring colder temperatures into an upper level ridge? What do you think is going to happen here? All right, it has the opposite effect as compared to troughs. When you get this blue oval shape, this is your colder air advection coming into the ridge axis. By the way, look over here on the right, this ridge axis is represented by this sawtooth solid black line. The ridge axis is going to be that point of the ridge where your heights are the highest. So with cold air advection coming into a upper level ridge, it's going to basically weaken or flatten out this ridge. And with a decrease in amplitude as the ridge flattens, the speed of the movement of the ridge will increase. So cold air advection into ridges, upper level ridges, is the opposite effect of cold air advection into troughs. Okay, that's the big thing I want you to take away from this. So here it is again, cold air advection and ridge axis. Notice this ridge is moving to the east at 15 knots. What happens when you put the cold air in that ridge? It's going to weaken or flatten this ridge, and then the speed of that ridge is going to pick up or increase. All right, now let's examine atmospheric stability. Now, low-level stability, what does this refer to? It refers to a balance of the atmosphere and the vertical. Okay, so atmospheric stability, in a lot of cases, what we want for atmospheric stability is going to be a warm air mass. Remember WOC from a previous training video I gave you? What does that stand for? Warm air over colder air. So we want warmer air, it's the W, over colder air. So let's say this is the surface, cold air at the surface, warmer air aloft or above that. We like that. The atmosphere likes that because the warmer air is lighter and it wants to rise. The colder air is heavier and it wants to sink. So there is no mixture in the vertical, there's no vertical air current setting up because we have a balance or atmospheric stability. Now, unchecked upward vertical motions, let's say this doesn't exist, the warm over cold. Now let's go over here on the right, and let's say now we have the cow. Remember, don't tip the cow. We use the acronym COW, colder air over warmer air, okay? So in this case now, let's say we have warm air at the surface and we have colder air aloft. Warmer air is going to be less dense, so it's going to want to rise in the vertical upward. Colder air is going to want to sink. So we have, colder air sinking, warm air rising, and that is an example of unchecked upward vertical motions. And if you have sufficient moisture in that case, it can produce poor weather conditions with this unstable atmosphere over here on the right. In most cases, it's going to produce clouds and some sort of precipitation. In some cases, it produces thunderstorms. Now, if downward vertical motions are prevailing, this would put a cap on cloud development, thus giving good weather. And that has to do more with this on the left. Why I drew the WOC, the warm over cold, the walk. We have downward vertical air motion going on over here. We have no mixing of these two air streams or air currents. Now, what happens when we add cold air advection, cold air moving in the lower levels of the atmosphere? What happens to the stability of this vertical column of air? First thing first, due to its greater density, guess what? Colder air is going to want to sink. So we put colder air in the low levels of the atmosphere, okay, closer to the surface. Cold air advection at low levels, it does not move upward. It's going to sink and get closer to the ground. So if we have cold air advection in the low levels of the atmosphere, it does not have the ability to rise. And this is going to result in increasing, we're going to increase our atmospheric stability in this case. A good example of this is when we get a cold polar high pressure system moving into an area from Canada during the wintertime. With this type of high pressure, there is cold air advection near the surface. Typically that cold air advection is going to be out ahead of this polar high pressure system moving into the middle latitudes. Okay, and you're going to get stronger northerly winds initially out ahead of that surface high pressure system, and then as the surface high settles over your area, your winds are going to become much lighter and in some cases calm. But in general, what you're going to get with polar high pressure, with the cold air advection moving in closer to the ground or the surface of the earth, you're going to get more stability, downward vertical air motions. You're going to get improving weather with polar high pressure. I've witnessed this myself, where you just see some amazing crystal clear blue skies when you have that continental polar air mass in place. You got the polar high kind of moving in from the west, and you get some really chilly temperatures out ahead of the high pressure system. This is totally true what happens in the atmosphere. It's really amazing when you put the Y with this cold air advection low levels and the increasing atmospheric stability. You put that Y behind the what happens. Now, what happens when we put cold air advection in the upper levels of the atmosphere? What happens to the stability in the upper levels of the atmosphere? Well, it's going to be the opposite, right? It's going to be the opposite of cold air advection in the lower levels. We say cold air is heavier and denser. It wants to be closest to the ground. So with cold air advection, represented by the letter CAA in this diagram on the right, look at this black arrow. You see the downward directed black arrow here. That's showing that heavier, denser, colder air is trying to sink towards the surface. And as it sinks towards the surface, it displaces other air at the surface upward around it. So cold air advection in the upper levels of the atmosphere displaces the surface air upward. This is an unstable situation. This is the cow situation where you get colder temperatures over warmer. So in this case, we're going to call this the cow, right? Don't tip the cow, because you tip the cow, that cow is very unstable. So we got, warmer air are these black arrows here are warmer air streams. Air is rising upward. Colder air is sinking right down here in the center because it's heavier and denser. All right, so an example of this, by the way, if you were to do an experiment at home, think about this. Take some vegetable oil and some water, mix it together in a cup. All right? If oil was already in the cup, so let's say you put the oil in the cup first. Pour the oil in the cup. Pour just a little bit of it, right? And then you pour cold water into that cup. The cold water is going to be denser and it will sink to the bottom, displacing the oil. The oil is going to rise to the top because of its lesser density. So you can actually do this. The oil would represent the displaced warm air rising on this example on the right to the top of this cup. So if you want to do a cool science experiment, I highly recommend you take cooking oil or some kind of vegetable oil, pour it first into a cup, just a little area of it, don't fill it up, and then pour some water on top of it. And you can literally mimic or imitate the atmosphere with the oil being lighter. Oil would represent your warmer air rising to the top of the cup. And when you pour cold water into the cup on top of the oil, you're going to see the oil rise because it's less dense, the cold air sink. And there you go. So you can actually imitate this right at home with some simple things. A cup, cooking oil, and then some cold water from your sink. All right, so just as a review for cold air advection, what does cold air advection do? Okay, first of all, we look at the whole vertical atmospheric column. Cold air advection, or cold air moving in, causes upper level height falls because the air wants to sink. It also causes surface pressure rises because the air, as the air sinks, it adds more surface pressure, more weight to the surface, and that's going to cause pressure to rise. Now, if we put cold air advection into the trough axis, remember, this is what a trough wants, and it wants to deepen and get stronger. So you put cold air advection into it, and it's going to do that. It's going to deepen. The amplitude is going to increase, and the trough speed of movement slows as this trough deepens. Cold air advection into the ridge axis, on the other hand, is going to weaken or flatten that ridge. And because that ridge becomes less amplified, it's going to speed up in its forward motion. Now let's switch gears to warm air advection, and let's see what warm air advection does for us. Warm air advection is simply the flow of air from a warmer place to a colder place. This causes upper level heights now to rise with warm air advection, and surface pressure is going to fall. So if we move or advect warm air into a vertical column of air, the less dense warm air is going to cause the column to expand upward. And this creates an overall upward vertical motion, causing heights to rise in the upper levels of the atmosphere. Now, I'm going to show you this now, okay? So we have warm air advection, or warm air moving in. Okay, it's moving in, represented by the letters WAA. Now, in the upper levels of the atmosphere, warm air advection is going to cause the upper level heights to rise. Why is that? Why do you think that's the case? Well, warm air is generally going to be less dense. So it's going to cause more of a dome-like shape. Warm air is very similar to a dome, okay? The upper level heights are going to rise because the atmosphere is so much more expansive with warmer air. And then the surface pressures over here on the bottom right are going to fall, and that's really because the warm air, again, is less dense, so it wants to rise upward in the vertical, okay? What happens when we take warm air advection? What happens when we take warm air advection now into the upper level ridges? We put warmer air into this upper level ridge on the right. Now, ridges are associated with higher heights aloft. With warmer air moving into that ridge axis, guess what's going to happen? The ridge is going to like that. The upper level ridge likes warmer air moving into it. The heights are going to rise further. This is referred to as a building ridge situation, and we're increasing our amplitude once more in this situation. Now, a building ridge is going to have a tendency to slow down an overall speed of movement. All right, so take a look at this graphic on the right. So initially we have our warm air advection represented by this red oval. We have the ridge axis. This is black sawtooth line here. So the warm air is moving into the ridge, and then guess what that ridge is going to do? Look at over here on the right. Look how much more amplified this ridge is. Increased amplitude, which is the increased vertical distance here, right? That's your increased amplitude there. And this overall movement of this ridge as it propagates or moves to the east is going to slow down when you have amplified a ridge like this. Now, what happens with overall? Let's take a look at this. We're going to now take a look at what happens when we put cold air advection into the trough. Wow, okay, I have a typo here and I apologize. All right, so this should actually be the opposite, I believe. Let me just verify. Yep. Yes, it should, everybody. So this what we just covered is absolutely right. Warm air advection of the ridge is going to build the ridge and make it stronger. Now, this should be cold air, not warm air. What happens if we take colder air advection into upper level ridges? And this is what happens when you put together all these slides, and you're just playing around with the wording a little bit. So I want you to realize then that this warm should replace with a cold. So let me draw this out, and I do apologize for this oversight on my part. So we're going to put a line through warm. We're going to say cold air advection. So cold air advection, because we've already discussed warm air advection into a ridge. We already discussed the warm air advection into the ridge. So now let's talk about the warm air advection into the trough. Okay, sorry again, I apologize. I'm getting mixed up here in my mind. So it is warm air advection, apologies. We are looking at warm air moving into a trough here. All right, it's not cold, so disregard what I just said. This is warmer air advection into upper level troughs. So we examined warm air advection into ridges. Now we'll look at warm air advection into upper level troughs. Again, my apologies. I should have trusted my wording, and it just didn't seem right, but it is right. Okay, so let's talk about this. Warm air advection in upper level troughs. What is going to happen here? All right, it's with warm air advection, remember that it's going to result in higher upper level heights. Well, what is a trough? A trough is lower upper level heights, right? So if I bring this over here in this graphic on the right, if I bring this oval red shaped color here, warmer air into this base of this long wave trough, let's just say it's a long wave trough. All right, warm air advection is not what an upper level trough wants. It wants cold air advection. So what's going to happen over time is it's going to weaken this upper level trough. If I put warm air advection on an upper level trough, it's going to weaken the trough, or a decrease in amplitude, and that's going to cause the weakening ridge to speed up. Yeah, something's not right here. But anyway, it should be, this should be weakening trough to speed up, not weakening ridge. Wow, I am really off on this. Again, I'm sorry for this, guys. So this should be not a ridge. This should be a trough. Because we're talking about warm air advection and troughs on this slide, okay? So you see it over here, warmer air moving into the trough axis. The overall initial speed initially with a more amplified trough is 15 knots to the east. And then over time, we get that warm air advection in there. And you notice how much more flatter this trough is. It's not as amplified. And that's going to result in faster movement to the east. Decreased amplitude, filling trough. Again, apologize for this slide. Wow. All right, so now let's examine warm air advection and stability in the low levels of the atmosphere. Okay. Let's examine this next. So if I have warmer air moving into the lower levels of the atmosphere, warm air is going to be less dense. It's going to want to rise in the vertical. And if you get enough moisture present with that rising warm air, clouds are going to form. And this is going to result in decreasing stability. But if I put warm air advection into the upper levels of the atmosphere, that's going to actually increase my stability. So we have warmer over a colder situation, and this is going to increase my stability. So hopefully this should make sense. This is the case of, in this case, we have walk. Warm over cold. Warmer air over colder air below it. And that is going to, basically in the upper levels, you bring warm air advection, those upper levels, is going to increase the stability. All right, now, what about the strength of temperature advection in general? Like, let's take a look at what really determines the strength of temperature advection. It's really going to depend on many factors. First thing it's going to depend on is the strength of that pressure gradient force, which directly ties in with the strength of your wind speeds. The stronger the pressure gradient force means that we have a greater pressure difference over shorter horizontal distances. So greater pressure changes basically over shorter distances yields a stronger pressure gradient force. And when we have a stronger pressure gradient force, we have stronger winds, and that's going to result in stronger temperature advection. Specifically when we have the orientation of our isotherms and our isobars or height contours perpendicular to each other. I'm going to show you that here in a moment. So isotherm, or lines of equal temperature, the spacing of those isotherms, whether they're tightly packed or loosely packed, that really determines your temperature gradient. The orientation of the isotherms in relation to isobars or height contours is very important to look at. So if your isotherms or lines of equal temperature are perpendicular to those isobars or height contours, the chance for strong temperature advection is greatly increased. The best scenario for strong temperature advection, by the way, is strong winds blowing perpendicular to these isotherms with a strong pressure gradient. Here we go. Now this is what I wanted to show you for strength of temperature advection. These red dashed lines here represent your lines of equal temperature. So they range from +5 They're 5 degrees Celsius increments from +5 all the way to +25. Now, if I were to have the wind blowing perpendicular like this, if my wind is blowing perpendicular basically across these isotherms, it's going to basically blow warmer air into this area here where I mark the X. Warmer air advection, WAA, is moving in to this location because I have a perpendicular wind component. I also look at the spacing of these isotherms, and you notice how tightly packed they are. I mean, we're going from +5 degrees Celsius to +25 degrees Celsius over a pretty short distance. One thing that's missing out of here would be your isobars. So let's say that low pressure is back here. This is an L here. This is your low pressure. And let's say you have warm air advection going on here. So let's basically say that your isobars are going to be orientated like this. These solid lines are your isobars around that low pressure. Okay. Notice this perpendicular relationship here of the isobars, these red solid lines here around your low pressure. If that's the case, these isobars are perpendicular to your isotherms, you really are going to get some strong temperature advection in this case. Right, so warm air advection review. Warm air advection, what does it do? It causes upper level height rises because the atmosphere is more expansive, it's less dense in the vertical. Causes surface pressure falls as the air rises up away from the surface. And then warm air advection into the upper level ridges, it's going to build the ridges and it's going to slow their speed of movement because it's becoming more amplified. You're going from a ridge like this to a ridge like that, okay? It's going to be slower movement when you have a much more amplified ridge like that. Warm air advection, meanwhile, into the troughs, it's going to fill troughs. Upper level troughs like cold air advection. They don't like the warm air advection coming in because that really will cause them to fill. And then when you have a filling trough, it's going to speed up. So warm air advection into a trough. Let's say our trough is initially like that. And then with warm air advection coming in, let's say this is your warm air advection coming in, it's going to the base of this trough. It's going to basically flatten or weaken your trough like that. And it's going to cause it to speed up when it flattens. Now that we've talked about cold air advection into troughs, upper troughs, we've talked about cold air advection into upper level ridges. We talked about warm air advection into troughs and warm air advection into ridges in the upper levels. We talked about the stability of cold and warm air advection, both in the low levels of the atmosphere and the upper levels of the atmosphere. So now we're going to end today's training video and talk about measuring pressure. Okay? There are 5 different terms I want to just introduce you to for measuring pressure. There's something known as station pressure, there's something known as sea level pressure, the altimeter, pressure altitude, and density altitude. So let's take a look at this. All right, so station pressure, what is this about? This is the pressure that's not adjusted for elevation, and it's not used on surface weather maps. All right, it's measured using a barometer. A barometer measures atmospheric pressure, typically in units called inches of mercury. The most common type of barometer that we see is the aneroid barometer, which does not contain any fluid. The aneroid barometer uses a small partial vacuum cell within it that expands and contracts as it reacts to pressure changes. All right, so station pressure. Why do you think we don't use these on weather charts? Well, if you look at the Earth, we know it's not just completely flat. There are going to be areas of higher elevation, mountainous areas across the Earth. All right, station pressure, if we were just to look straight up at station pressure in inches of mercury, you would notice there'd be a major difference at the station pressure at sea level versus the station pressure at higher elevations. The station pressure at higher elevations at the tops of some of these peaks, these mountains I'm showing, is going to be much less, okay? In fact, if we go up to this top of this peak here, our pressure might only be 14.765 inches of mercury. A little bit lower in elevation, it might be 25 inches of mercury. Down at the surface, it might be 29.92 inches of mercury. So as you can see, as you go upward in the atmosphere and climb an elevation, specifically on mountains, your station pressure is going to fall. All right, so we can't really compare the pressure at multiple locations if we don't somehow correct for this station pressure and correct for this elevation change. So we want to, when we compare a surface weather chart, we want to compare the pressure, basically correcting station pressure for sea level pressure. That's what I'm going to talk about next, is sea level pressure, okay? We want to correct for the altitude, for that station pressure, those differences based on altitude or elevation above sea level. So we use something called sea level pressure. Now this adjusts that station pressure I just showed you at different elevations and allows for comparison of pressure. It adjusts from station pressure. Corrections are made for altitude as well as temperature, and these corrected values are then encoded in millibars on surface weather maps. Millibars is another unit that we look at for, it's another unit of pressure. Now from these values, the lines of equal pressure are known as isobars. These can be drawn out to depict the current weather. We can actually draw these out in a surface weather chart and do a surface weather analysis by taking and converting station pressure, adjusting for the altitude, the elevation, as well as the temperature, and coming up with a common sea level pressure amongst all stations, no matter how high or how high above sea level they are, or whether they're at sea level. And by the way, the sea level pressure is abbreviated with the letters SLP, and it's used to help forecast altimeter settings. Speaking of altimeter, what does this mean? What is an altimeter? It's an aneroid barometer set to convert atmospheric pressure to an approximate elevation. Now this is very important in the aviation industry. They use altimeter readings because it helps them to determine the flight level the plane's flying at. So using an altimeter, this aneroid barometer, which converts atmospheric pressure to approximate elevation, using the altimeter, aircraft will fly at a constant pressure surface, and not at a constant altitude. If flying from warmer air to colder air, the constant pressure surface will get lower, closer to the Earth's surface. This decreases the plane's altitude. Now this is very important right here, this fourth bullet, because if an airplane is flying in a mountainous area, all right, you know that the mountains extend well above the Earth's surface, and if you're going from a warmer air mass to a colder air mass, the constant pressure surface will be lower, closer to those mountains. And it's actually going to decrease the plane's altitude, and it could put the plane in a very bad situation if they don't have the right altimeter setting to account for these temperature changes. To compensate for temperature changes in flight, what typically happens are pilots are going to regularly radio for new altimeter settings to the air traffic controllers. One of the other things that we use, that aviators use specifically, is called pressure altitude. It's abbreviated PA. Now pilots are going to use this altitude to compute pressure to actual elevation when taking off and landing. This determines the adjusted altitude needed for safe operations. So pressure altitude must be known for computing density altitude. That's the next one I'm going to talk about. Density altitude is the altitude in the standard atmosphere portrayed by the known air density in the present atmosphere. Basically, you're comparing current density with the average density of where they're flying. The DA is computed from pressure, altitude, and temperature. So the two things that really come into play to calculate this density altitude for pilots is the pressure altitude as well as the temperature. So it's very important for pilots when they're taking off specifically or landing, how much lift and thrust are needed for these takeoffs, how much is needed for climbing, and how much cargo. Pilots make a decision on how much cargo they weigh down in the plane based on this density altitude. All right, so a couple rules of thumb with density altitude. The altitude and temperature will determine that density altitude. These are the two things that really come into play for density altitude. And now let's look at the relationships here. Increasing altitude is going to decrease the density. The higher the plane gets on its climb, you're going to have lower density. And in that case, the density altitude will increase. Increasing temperature is going to decrease density as well. Warmer air is much lighter, so it decreases the overall density, and that is going to result in the density altitude increasing. And then a higher increasing density altitude is going to decrease an aircraft's performance with that decreased density. With decreased density, this is what happens with a plane. The plane is going to require a longer takeoff roll. It's going to decrease the ability of the plane to climb. And with decreased density, you reduce the amount of payload, how much weight an aircraft can carry. So these are very important when we talk about the aviation industry. We talk about altimeters being that aneroid barometer. It's set to convert atmospheric pressure to an approximate elevation. And for pressure, for the altimeter in general, pilots are flying at a constant pressure surface, not a constant altitude. We talk about pressure altitude here. Using altitude to compute pressure to actual elevation when taking off and landing. And we talk about density altitude. All right, so review of pressure. Last slide of today's training video. Station pressure is the actual pressure, but again, it's going to widely vary depending on elevation. The higher up you go in the atmosphere, you go up to the top of a mountain peak, for example, you're going to have lower station pressure as compared to a location at sea level. So to compare every location on the weather map, we use sea level pressure, which is adjusted station pressure down to sea level. And this additionally, we talked about altimeter. For pilots, converts pressure to elevation and altitude. Pilots also use pressure altitude, which is elevation correction for the aircraft. And then we have density altitude. Increasing the density altitude will decrease an aircraft's performance. So very important to take a look at all these parameters. All right, that wraps up my training video. This was part 2 of pressure and temperature advection. Let's just do a quick review here of what we looked at for part 2. We started off with cold air advection. We talked about what cold air advection was. Basically, you're bringing colder air into a location. And when winds cross lines of equal temperature isotherms, you have temperature advection taking place. All right, and since colder air is denser, tends to sink, upper level heights fall with cold air advection. Sinking air results in increased surface pressures. For cold air advection of the column, we now know that upper level heights fall because the colder air aloft wants to sink. And we also know that we get downward vertical motion with cold air advection, and that is going to result in increased surface pressures. We talked about cold air advection in upper level troughs. It's going to deepen the troughs. As the troughs deepen, the overall forward speed of movement is going to slow. We looked at cold air advection at upper level ridges. Upper level ridges are generally going to flatten out or weaken when we put cold air advection into them. And with that decrease in amplitude or the flattening of the ridge, that ridge is going to move quicker to whatever direction it's heading. We looked at atmospheric stability. We looked at warm over cold on the left. We looked at cold over warm on the right. Warmer over colder air is a more stable atmosphere. Colder over warmer air is a much more unstable situation. And then we looked at cold air advection at low levels. It's going to increase stability because the air is heavier and is close to the surface where it needs to be. We talked about cold air advection at the upper levels. That's going to basically decrease the stability of the atmosphere. Cold air in the upper levels, colder, heavier air is going to want to sink towards the surface. That's then going to displace the air that was at the surface upward in the atmosphere. Again, we can do that oil and water experiment if you want to try it out. With the oil in the cup already, pour some cold water into that cup and watch the oil rise to the top. The oil would be your warmer air, would represent the warmer air, and the cold water would represent the colder air. And then we looked at the review of that, and now we'll move on to warm air advection review. Again, warm air advection is the flow of air from a warmer place to a colder place. Warm air advection generally results in upper level heights rising because the atmosphere is going to be much more expansive with warmer air, and surface pressure will fall as the air rises away from the surface. What happens, here we go graphically, warm air advection, warmer air moving in, upper level heights will rise, and surface pressures will fall. With warm air advection into these upper level ridges, we generally get upper level ridges love the warm air advection. That causes these ridges to get stronger or to build. As these ridges build in amplitude, increase in amplitude, they slow down in forward motion. And then warm air advection into upper level troughs. We get warmer air into the base of a trough, for example. It's going to result in a filling of the trough. less amplified or lower amplitude trough over time with warm air moving into the trough. And this is going to result in a speeding up of the trough. Warm air advection in the low levels of the atmosphere results in instability or unstable atmosphere because warm air at the surface is lighter and wants to rise. If it rises and have enough moisture present, you get clouds and in some cases precipitation. Warm air advection in the upper levels, on the other hand, increases your stability because you have a warmer air layer over a colder air layer. And then strength of temperature advection, the packing of these red dashed lines here, these isotherms, really matters. When they're tightly packed, we have a strong temperature gradient. When they're more loosely packed, or these red dashed lines, these isotherms are farther apart, we have a weaker temperature gradient. But generally what we want is we want a perpendicular component of the isobars, lines of equal surface pressure, to these isotherms. And if we have a perpendicular wind flow across these isotherms, we are going to have some sort of temperature advection. And then we talked about just a review of warm air advection again. And then we talked about how, different terminology associated with pressure, station pressure, sea level pressure, altimeter, pressure altitude, and density altitude. All right, that wraps it up, everybody. I hope I didn't confuse you. I feel really bad about this one here. I really feel bad about that slide, but I hopefully clarified it for you and you understand really what I was trying to get at here. Warmer air moving into upper level troughs. It's going to basically fill or weaken the troughs, okay? Troughs, upper level troughs like colder air advection. All right, that wraps it up. I still got plenty of great training videos that are ahead. I certainly hope you enjoyed this presentation. Until next time, everybody, take care and God bless.